3, given f of x equals 2 cosine of x minus cosine squared of x, find the intervals on which f is increasing and decreasing. Find local maximum and minimum values of f, and find intervals of concavity and inflection points. Now, with trig functions, ideally you have an interval. Don't have an interval here, so keep in mind we're going to get infinity answers. The way we get infinity answers for cosine or sine, and also secant and cosecant, is we're going to add 2 pi n, where n is an integer. For tangent and cotangent, we're going to add pi n, where n is an integer. Okay, that's how you get infinity answers. You find the answers on the basic 0 to 2 pi interval, and then you add these numbers. For tangent and cotangent, you simply need one answer. For sine, cosine, secant, and cosecant, you need 2 answers. All right? So keep that in mind that we're going to be getting infinity answers. It's up to us to establish what those answers are, and then we want to create a pattern to represent the solutions to these types of problems. All right? So the intervals on which f is increasing and decreasing is going to be infinity intervals. Okay? We're not going to write infinity intervals. We just need to establish the pattern of it's increasing, then decreasing, then increasing, or maybe it's increasing, increasing, decreasing, decreasing, whatever. There'll be some pattern to it. We'll find it, and then we'll be able to establish that pattern. Same for local maximum minimum values. There'll be infinity of them, but they'll happen. It'll keep on going to the same point. So highest point, lowest point, highest point, lowest point. So that'll be pretty doable. Intervals of concavity inflection points, again, there's going to be infinity of them, so we're going to have to use this type of notation to establish those intervals. So let's take a look, and I just need to shrink that up because it's going to get in the way. Okay. So first off, if you recall from last week, A and B, the intervals of increase and decrease and the maximum and minimum values of f all have to do with the first derivative of the function. So these have to do with f prime of x, where the concavity stuff has to do with the second derivative. My personal preference, I like to go ahead and find the first and second derivative right off the bat, so I know what they are. That way when I need to refer to them, I've got them on my paper already. So if I do f prime of x, keeping in mind that f of x is 2 cosine of x minus cosine squared of x, it's a basic trigonometric function. 2 cosine of x is just a cosine function. This is going to be a chain rule because it's cosine of x squared. So we have to do the power rule first, and then we have to differentiate cosine after that. So the derivative of 2 cosine of x is just going to be negative 2 sine of x. And nothing weird, pretty basic. For the cosine squared, remember the cosine squared means cosine of x, the whole thing squared like that. So it looks like that in reality. So if I power rule that, 2 is the power being multiplied by negative 1, so I get negative 2 cosine of x to the first power. And then since it's still cosine of x to the first power, the base is not x, it's cosine of x. We have to multiply by the derivative of that, which is negative sine of x. That gets me f prime of x, not simplified completely. If I go ahead and simplify completely, f prime of x is going to equal, let's make this first, so positive 2 cosine of x sine of x minus 2 sine of x. Alright, so there's my first derivative, and I have that over here somewhere. Alright, and then if I want to do f double prime of x, I have to differentiate f prime of x, right? So f prime of x is this expression. This is a product of functions, so the product rule is necessary. That's just a basic trig function. So f double prime of x. If I do the product rule first, I'll call that function 1, that function 2. I'm going to get 1 d2 is going to be 2 cosine of x times d2 is going to be cosine of x. Plus 2d1 is going to be plus sine of x times derivative of 2 cosine of x, which is negative 2 sine of x. And then the derivative of 2 sine of x minus 2 sine of x is going to be minus 2 cosine of x. So I get 2 cosine squared minus 2 sine squared minus 2 cosine of x. So f double prime of x, 2 cosine squared x minus 2 sine squared x minus 2 cosine of x. Now, keep in mind when we're trying to find critical numbers, we're going to try and solve for this thing equal to 0. We're going to try and find where it's undefined, find endpoints, right? Well, cosine and sine aren't undefined, and there are no endpoints. So basically, we just have to find where these things equal 0. All right? If I'm going to solve a trig function, it's helpful if cosine, sine, cosine, if all three of these were the same trig function. All right? Obviously, these aren't either sine, sine, cosine, but to the first power, it's a little bit more challenging to make one become the other. In the second power, it's real simple. Sine squared is the same as 1 minus cosine squared, right? So if I did that, 2 cosine squared of x minus 2 times 1 minus cosine squared of x minus 2 cosine of x, like so. Minus 2 times minus cosine squared makes 2 cosine squared, plus 2 cosine squared makes 4 cosine squared of x. Then minus 2 cosine of x, and then minus 2 times 1 is minus 2. This expression is the same as that one, but this one only has cosine in it. It's a more powerful derivative. It's more powerful, more useful for us. So I'm going to go with that structure there. So f double prime is going to be 4 cosine squared of x minus 2 cosine of x minus 2. Right. For me personally, if I'm looking at your work on your paper, I don't need to see where you did this. You can do that on a scratch sheet of paper somewhere else out of the way. If you want to isolate, keep in this problem what I really need to see. I need to see that you figured out the first and second derivatives and you have them somewhere marked on your paper. As far as how you got to this point, I'll believe you did a derivative because we've already done like 8 or 9 sections worth of derivatives, right? Practicing a lot. Okay, I don't need to see you go all the way through the process to get the derivative anymore. Give me the derivatives. I'll trust you did that on your own. Okay? Once you get to this point, the point of this lesson, this chapter, is being able to identify all this stuff off of this information. That's what we're doing. We're trying to use the derivatives in order to establish information about our graph. So, find the intervals on which f is increasing and decreasing. So I need to find critical numbers of the first derivative. So again, 2 cosine of x sine of x minus 2 sine of x. The 3 criteria are equals 0, undefined, and endpoints. Sine and cosine aren't undefined. There are no endpoints. So the only thing we have to concern ourselves with is the first derivative should be equal to 0. If it was a secant, a cosecant, a tangent, or a cotangent, those are undefined occasionally, right? Like tangent of pi over 2 is undefined. Cotangent of 0 is undefined. Secant of 0, that's right, secant of pi over 2 and cosecant of 0. And then, you know, every time the sine or cosine equals 0, either tangent or cotangent or secant, cosecant is undefined. All right, sine and cosine aren't undefined ever, so if you have those, all you have to do is do the equal 0 thing. Now I forgot this 2, didn't I? There we go. All right, don't forget the 2, that's important. All right, so what I'm looking at here is a trig function equal to 0. I'm supposed to solve it. And one or two things are going to happen here. Either you can solve it pretty easily using algebra or you can't. Okay? If you can immediately see an algebraic way to do it, I recommend that. Notice 2 sine of x belongs to both of these objects, right? So if I've got a common factor of 2 sine of x, and if I factor 2 sine of x out of there, I get 2 sine of x times cosine of x minus 1 equals 0. Now, I just got done saying with this second derivative, if we can get everything down to one trig function, it's helpful, right? And there's no way really to do that in this problem, but I've broken it down into a factor with sine of x and a second factor with cosine of x. That's useful too, if I can separate those factors. Because once I get those factors separated, then I know that either 2 sine of x equals 0 or cosine of x minus 1 equals 0. If I can make either one of those things true, then that whole thing's going to be true. It's going to be a critical number. So, 2 sine of x equals 0 when x equals 0, and again when x equals pi. Sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, and so on. It's this repetitive thing here going on here. Cosine of x equals 0 cosine of x equals 1, because cosine of x minus 1 equals 0, move the 1 over. Cosine of x equals 1 at 0. Okay, we got a repeated answer there. If we try either one of those numbers out, let's try pi, for example, right here. Cosine of pi is -1. Sine of pi is 0. 2 times sine of pi is 0. 0 minus 0 is 0. All right. If we try 0, cosine of 0 is 0. Sine of 0 is 0. Sine of 0 is 0. We get 0 minus 0. We get 0. All right. So both of those numbers, 0 and pi, get the answers that are correct and make that whole thing equal 0. Again, I need to invent infinity answers. Typically, we take answer 1 and add 2 pi in. We take answer 2 and add 2 pi in. In this case, it just happens to go up pi at a time. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on. So if you establish a pattern that isn't specifically that, you're allowed to go with that. So the critical numbers for this one will be, for the first derivative, x equals pi n, where n is an integer. If you want to put 0 plus pi n, that's fine. But if you try it out, pick any integer. Tyler, pick an integer.
2 point.
That's not an integer. Integer. Non-fraction. An integer.
Oh, 3.
3. All right. 3 pi. Notice 3 pi would be the number that would make this equal 0, right? Pick another integer, Chris.
7.
7 pi makes that equal 0, right? If we pick 2, 2 pi makes this equal 0. It also makes that equal 0, or equal 1. All right. So the fact is that any integer times pi is going to be an answer to this problem, right? Again, typically we got the plus 2 pi n because typically we got answers like this, 1 here and 1 here, but these answers happen to be 1 here, 1 there, so pi, every pi, it repeats itself. Okay. That's atypical for sine or cosine, but it happens just occasionally. It would happen for 0 or pi if it should happen. All right. Otherwise, you get that answer 1 plus 2 pi n, answer 2 plus 2 pi n. All right, so that's what my critical numbers look like. And again, I'm looking for increasing and decreasing intervals, and I need to invent all these intervals all the way up to infinity, right? Negative to positive infinity. This is where it gets a little tricky. So what I would do probably is I would go ahead and pick some actual numbers. Let's say, let's go from -3 pi to -2 pi. And from -2 pi to -1 pi. And from -1 pi to 0, and from 0 to pi, and from pi to 2 pi. Pick some intervals, just some specific intervals with the specific numbers we have. Any integer times n, I started at -3, went up to 2. Right? Everything pi, right? So -3 pi to -2 pi, -2 pi to -1 pi, and so on. What I'm doing is I'm trying to establish some intervals here to get an idea of what my infinity intervals are going to look like. All right, so numbers between -3 pi and -2 pi. That's -6.28, -9.42. So let's go with -7. -6.28, -3.14. Let's go to -4. -3.14 to 0, -1. 0 to 1, 3.141. 3.14 to 6.284. Okay. So numbers within the interval. Nothing magical about them. Just approximations for pi, and then just pick something between them. And what I want to do is evaluate this expression here for each of these numbers there to determine if it's going up or down. So I'm going to type in my calculator, y1 equals 2 cosine of x, in parentheses, sine of x, in parentheses, minus 2 sine of x, in parentheses. Oops. All right. Verify they're the same. I'm going to go to my mode, make sure I'm in radians, not degrees, because calculus we use radians, not degrees. And I just want to type in these 5 numbers: -7, -4, -1, 1, and 4. And I got positive, negative, positive, negative, positive. Right. so what I want to do is establish this pattern, and we can see it's just a repetitive pattern, goes up and down, then up and down, then up and down, and so on, right? And the fact that it's doing that with these numbers, if I went 7, my guess is going to be negative. Let's try it out, 7, negative, right? So it's doing that, it's going up and down and up and down and up and down. So I got the feel for what's happening here. What I need to do is establish an interval here. It's increasing here, 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 decreasing there and there. And what I want to establish based on this is what the answers look like. Odd to even up, even to odd down. Odd to even up, even to odd down, odd to even up, even to odd down. So if we're going from an odd pi to an even pi, we're going up. If we're going from even to an odd pi, we're going down, right? So how do I write that? It's increasing. Let's go from A to B. I should say odd instead of even. If A is an odd number, odd number pi, and B is an even number pi. Okay. That would be a legitimate way to write this to demonstrate what's happening for this function. So if I'm trying to graph this and I want to know what happens between negative 93 pi and negative 92 pi, I know it's going to be increasing because that's what's happening, right? Odd to even pi. It's decreasing, let's say from C to D, or let's even go from B to A. Now let's go C to D. I don't want to get confused here. So A and B are at even and odd, just in general odd and even power. It's decreasing when we start even and odd, so C is an even power pi, even number pi, and D is an odd number pi. So again, that's just a matter of setting up those. So that answers question A. Okay. Any work you do along that line will help me understand that. All right. When it comes to a quiz or a test, I don't give you an infinite thing like this. I'll give you a specific interval for a cosine or sine graph. Go from here to here. So you just have to do as many intervals as necessary for that, and you'll have specific answers. But again, in the homeworks, occasionally you'll get these infinite things. That's how you handle it. Local maximum minimum values. Okay, so we know it's going up to the maximum here, then it goes down to a minimum here, up to a maximum, down to a minimum. Right? So the maximums occur at the even number pi's and the minimums occur at the odd number pi's, right? So again, looking at this, again, if it goes up, then down, it hits the top, down, then up, it hits the bottom. Maximums happen at evens, minimums are happening at odds because that's what's happening, right? Again, all the way to infinity. There's infinity answers, I can't write them all out. But what I can do is figure out this. If I can figure out what the answer is right here and right here, that's what the answer is going to be every single time. Repetitive pattern. So, as far as maximums and minimums are concerned, we have a maximum of something at x equals even number pi, and a minimum of something at x equals odd number pi. Right. To find the actual number, we simply have to stick an even number pi or an odd number pi in the original problem. So, I'm going to do 0. What's cosine of 0? Cosine of 0 is 1. So it'll be 2 times 1. And cosine of 0 is still 1, right? So it'll be minus 1. 2 minus 1 is equal to 1, right? So maximum value of 1 at x equals even number pi. And if we do an odd number pi, let's do pi. Right? 1 pi is odd pi, right? Cosine of pi is?
Cosine pi is 0.
Zero's here, pi's over here, right? Over there. Unit circle, so positive 1, 0, negative 1. All right, cosine of pi is negative 1, cosine of pi is negative 1. Negative 1 squared is positive 1, right? So we get negative 2 minus 1, which is negative 3. So minimum value of negative 3 at any odd number pi. All right, so just like that, we've done parts A and B. Figured out all the increase and decreasing intervals along with the minimum and maximum values. All right. Finally, intervals of concavity inflection points come from the second derivative. I'm going to go to a new sheet of paper here. Do all that in red. All right. Second derivative. We have 4 cosine squared of x minus 2 cosine of x minus 2 equals 0. Now, we're trying to solve that thing. All right, it's a quadratic informed structure, so the quadratic formula is allowed to be used. If I do the quadratic formula and type in 4, negative 2, negative 2, I get cosine equals 1 and negative 1/2. Okay. Keep in mind if something is quadratic in form, you're not finding what x equals, you're finding out what this thing equals. And then if you know what that thing equals, then you have to solve that using other techniques. So x is going to be the inverse cosine of 1, x is going to be the inverse cosine of 1/2. Cosine equals number, x, cosine of x equals number, x equals inverse cosine of those numbers. So cosine equals 1 when x equals 0. Cosine equals 1/2 when x equals pi over 3. And again at 5 pi over 3. So we get a total of 3 answers there. Every one of those answers repeats itself every 2 pi radians. So for each answer we're going to add 2 pi. So 0 plus 2 pi n, or n is an integer, pi over 3 plus 2 pi n, where n is an integer, 5 pi over 3 plus 2 pi n, where n is an integer. The difference between what happened here and what happened over there was, the other one was 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, just every integer pi, right? So we have a plus pi n pattern. If I add 2 pi to pi over 3, we get 7 pi over 3, which does not match 5 pi over 3. So again, that's what usually happens. Usually get answer, in this case we got an answer here and here. Okay, and if you add 2 pi to either of the answers, you don't keep on hitting those same answers. So that's what our answers are. And again, I have to create intervals for this situation. If I just listed a few answers like this, 0, 2 pi, 4 pi, this is pi over 3, 7 pi over 3, 13 pi over 3. This is 5 pi over 3, 11 pi over 3, 17 pi over 3. That's what those answers look like. And every time you hit any one of those answers, you're hitting a concavity switch, possibly. Okay, so that's all the numbers we have to consider when we're doing this. All right. Looking at the size of these numbers, this, then this. Oh, hold on. That's right. This. That's the order of numbers as far as size is concerned. Pi over 3 is less than pi over 3. Pi over 3 is less than 2 pi, which is less than 7 pi over 3, less than 11 pi over 3. Okay, so it's just, that's how the numbers grow in size. So 0 to pi over 3, pi over 3 to 5 pi over 3, 5 pi over 3 to 2 pi, 2 pi up to 7 pi over 3, 7 pi over 3, up to 11 pi over 3. and so, okay, that's just established a little bit of the pattern here so we figure out what's going on. And if I'm going to test these intervals, pi over 3 is a little bit bigger than 1, so let's go with 0.5. I don't want to go at 1, it's pretty close to what that is. A little bit bigger than 1, 5 pi over 3 is a little bit bigger than 5, so let's go maybe 3. 5 pi over 3 a little bit bigger than 5, a little bit bigger than 6, let's go 5.5. 6.28 up to, let's see, 7 pi over 3 is probably about 7 point something, let's go about 6.5 there. And 7 point something up to 11 point something, let's go 9. Right. You need the decimal approximations of those, just type pi over 3 equals on your calculator to see what you get. And what we're testing is this right here, to see what's going on with that. So, I go to y equals, I type in 4 cosine of x squared. To type in something squared, so type in 4 cosine of x and parentheses, that completes the cosine function. Hit squared, now you're squaring cosine, you're not squaring x. If I typed in cosine of x squared end parentheses, now I'm squaring x first, then cosine. This is taking cosine first, then squaring the result. So 4 cosine of x squared minus 2 cosine of x minus 2. I've got my test points here, 0.5, 3, 5.5, 6.5, 9, and it went negative, positive, negative, negative, positive. Okay, so that's not enough for me to establish a specific pattern here, so I want to go a little further. So let's go from 11 pi over 3 up to 4 pi to 13 pi over 3. And 13 pi over 3 to 17 pi over 3. Alright, so 11, a little bit bigger than 11, 12.56, let's go 12. 12.56 to something over 13, let's go 13 for that. And then something 13 to 17, let's go about 15 for that. So 12, 13, 15. And it goes negative, negative, positive. So I got my results here. I've got negative, positive, negative, negative, positive, negative, negative, positive. Okay? Does that look like a pattern to anybody? We have 3 answers at a time, right? There's negative, positive, negative for that set. Negative, positive, negative for that set. Negative, positive, probably negative for the next set, right? So it's negative, positive, negative every 3 times. It's negative, positive, negative. This answer 0 came from this answer. So from this answer to this answer goes down. From this answer to this answer goes up. And from this answer back to that answer goes down. It goes down, down, up, down, or down, up, down, down, up, down, down, up, down. So concave down, concave down, concave. There's got to be some concave up in there somewhere. Let's see. Concave down, concave down, concave up. So I'm imagining something looking sort of like that. Concave down to a point, concave down to another point, then concave up. So it's probably going to hit a flat point, then come back down, sort of like that. As far as how to write that, that'd be hard to write. Anybody think off the top of their head how to write that? Let's see here. We're taking these answers. Okay, let's do it this way. We're going from an answer here to an answer here, right? So here's how I'm going to write it. I'm going to write A plus 2 pi n, comma B plus 2 pi n, I don't have to write it that way. I can just write the actual numbers. 0 plus 2 pi n to pi over 3 plus 2 pi n. If I go from this answer to this answer, it's going concave down, right? And that represents all the answers from negative to positive infinity with that structure, right? All right. Then, let's see here. I'm also going concave down if I'm going from here up to here, right? So 5 pi over 3 plus 2 pi n to 0 plus 2 pi n. Or let's make it 5 pi over 3, 2 pi. 2 pi plus 2 pi n. I want to make sure this is bigger than that. So from 5 pi over 3 to the next number on the list, 2 pi. Both plus 2 pi n. Both of these are concave down. And from pi over 3 to 5 pi over 3, so 5 pi over 3 to 2 pi n, up to 5 pi over 3 to 2 pi n is concave up. Inflection points happen every one of these numbers, right? So I just need to figure out what this one and this one and this one are, and then everything else is just repeated one of those. So I want to type these three numbers into my calculator for my function. So if I typed in 2 cosine of x minus cosine of x squared, again cosine of x and parentheses squared, that's squaring cosine, not squaring x. And the three numbers I have are 0, pi over 3, and 5 pi over 3. 0.75, 0.75, and 1. Every one of those is an inflection point because of concave. Well, actually, that's not true. From here to here is an inflection point, right? From here to here is an inflection point. From here to here isn't. That's not, yeah, that goes from negative, negative stays the same. The inflection points happen at the pi over 3s and the 5 pi over 3s. So inflection points, pi over 3, comma 0.75. Oh, I want to have all of them, not just one. Pi over 3, comma 0.75 is 1. Pi over 3 plus 2 pi n, comma 0.75 is all of them. And 5 pi over 3 plus 2 pi n, comma 0.75 is the other one. So I got a lot of information there. Again, it's all infinite. What makes that challenging is the infinity part of it. Again, if it's said from negative 2 pi to 2 pi, it's easier. Again, if it comes to a quiz, that's what it's going to be. I'll give you endpoints, so you don't have to make infinity answers. Just start here and there. You'll probably get 8 or 9 intervals, but they'll be what they are. If I tried to graph this thing, window, let's go from negative 2 pi to 2 pi. Min is negative 3, max is 1. That's already set there, so hit graph, see what happens. Goes down. There's my concave up, concave down, concave down. So again, that's kind of what I was expecting there. The concave down to a point and concave down again. A lot of times when you get that concave down twice in a row or concave up, you hit a flat point, like hit a derivative of 0, but then instead of going up or whatever, it decided to go back down. So concave down like that. So that's what it looks like. Again, it's just a repeated pattern. So if I were to extend this out, let's go from negative 4 pi to 4 pi. It's going to be the same picture, just more of it. Again, with trig functions, you should expect that to happen pretty often, where just same pattern every single time, just a matter of how many you want to go. And for me personally, I'd probably just have you go from one value to another value. It takes all the infinity out of it and makes it a little easier.